In this video, we are going to see some of the probability distributions of interest. We'll start with a couple of discrete random variable probability distributions. The first one of which is a binomial distribution. An experiment many times consists of repeated trials, and each trial might have just two possible outcomes, such as success and failure. Such type of an experiment is generally called a Bernoulli process. For example, testing of products in an assembly line for defects. So either the product has a defect or it doesn't. If we consider that as success and failure of the trial, then the probability of success, which is probability of a random variable taking value 1, is equal to P, and the probability of failure is 1 minus P. In a Bernoulli process, the experiment usually consists of n number of repeated trials that are independent. So the trial doesn't affect the previous trial or the next trial. And each outcome of a trial is either classified as success or failure. The probability of success, which is P, it remains constant from trial to trial. Now consider a sequence of n independent trials of a Bernoulli process and let a random variable x denote the number of successes in the trial. So you're counting how many successes are there in the n trials, with probability of success being P. Now the distribution of such a random variable is called the binomial distribution, which is denoted as this, with the parameters n and p, n being the number of trials and p being the probability of success. The probability distribution of x is given as f of x of k is probability of the random variable x taking a value k is equal to n choose k times p to the power k and 1 minus p to the power n minus k. So this is the probability distribution or probability mass function for the random variable x, where n is the number of trials and k is the number of successes in those n trials, which can vary from 0, 1, 2 and so on up to n. Now let's see if the PMF is valid. So PMF is valid if the sum over all values of k is equal to 1. So we know using binomial theorem, this is the result for p plus q to the power n. Now since p plus q is 1, 1 to the power n is 1. So we can say that the PMF is valid. The binomial distribution looks like this, where x-axis is the value that the random variable x can take. Now this figure in A is for n is equal to 20 and p is equal to 0.2. The middle figure is for n is 20 and p is equal to 0.4. The third figure is for n equal to 100 and p is equal to 0.3. So the more the number of trials, the more is the number of successes in those trials. So you see a bigger spread. Now let's look at the mean of the random variable with binomial distribution. The mean is given by this formula. Now you can substitute f of k. So k times n choose k, p to the power k times q to the power n minus k. Now since for k equal to 0, this term is 0, we can change it, the summation, to start from k is equal to 1. And k n choose k is the same as n times n minus 1 choose k minus 1. This we have seen in the example where we are forming a team and we are choosing k players from a total of n players, and one of the k players has to be a captain. So you can either choose the k players from n and then one captain for the k players, so it's k times n choose k, or you can choose the captain first out of the n and then choose the k minus 1 players from n minus 1. So both of them are valid way of choosing, so they have to be equal. So k times n choose k is equal to n times n minus 1 choose k minus 1. So we made that substitution here. Now n and p don't depend on k, so we took n and one of the p terms out. So to get power k minus 1 for the term p. So these two are equivalent. And now we can replace k minus 1 with j and we get another binomial series. So np times p plus q to the power n minus 1. Again, this term is 1, so the mean will be np. Now let's look at another way of computing the mean. So we know that the random variable x is a Bernoulli process. So we repeat the same trial n times. Now if you consider a Bernoulli random variable y with probability p of success, then the mean of the random variable y, which is for a single trial, is k times f of k. So the random variable for a Bernoulli trial can be 0 or 1 with probability of random variable taking value 0 is 0. Sorry, probability of the random variable y taking value 0 is 1 minus p, but it's multiplied by k, which is 0. So this term disappears and you're left with probability of y is equal to 1, which is the probability of success, and that's p. Now the Bernoulli random variable is also known as an indicator random variable with the probability of success being p, and we can consider the Bernoulli random process or the repeated trials as sum of individual indicator random variables. So the random variable x can be written as I1 plus I2 so on plus In, where I is the indicator random variable showing if there is a success or failure in that particular trial. So the total number of successes, which is denoted by x, is the sum of the successes in each individual trials. So if you write x like this, then you can calculate the expectation of x by summing all the indicator random variables and taking the expectation. Since these are independent random variables, we can write it as the expectation of individual indicator random variables, and we already calculated that the expectation of an indicator random variable is p. So you're adding p n times and the expectation is np. So this is another way of calculating the mean of a binomial distribution. Now let's look at the variance of the binomial distribution. So for variance, we need the expectation of the square of the random variable. So let's first look at the expectation of square of a Bernoulli or an indicator random variable. So e of y square is 0 squared times p of y equal to 0 and 1 squared times p of y is equal to 1. This term disappears and you get p. So the variance of the binomial random variable, we already calculated e of x. Now we need to calculate e of x square, and we use the similar method of indicator random variable to calculate e of x square. So as we showed before, x is the summation of the indicator random variables. So e of x square is e of the square of sum of the indicator random variables. Again, we can separate them out by expanding this square. So e of I1 square plus I2 square up to In square, and then we have the combination of two indicator random variables, those terms. So 2 times E of I1 I2 all the way up to 2 times E of In minus 1 In. Now these are all indicator random variables with probability of success being P, and we already saw that E of y square is P, so we can replace each of them with P. So, so it will be N times P, and the cross terms we have 2 times N choose 2 times the cross term I1 I2. Now we need to figure out what is E of I1 I2. So each of them are an indicator random variable. So I1 I2 is also an indicator random variable, denoting that success in two independent trials. So this term becomes P square. So we get NP. If you expand N choose 2 times 2, you get N into N minus 1, and the expectation of I1 I2 is P square, because expectation of an indicator random variable is the probability of success, and the probability of success of this random variable I1 I2 is P square. Now we can calculate variance of x by substituting E of x square and E of x, which we already calculated. And the answer is NP times 1 minus P, or NP times Q, P plus Q being 1. So you can see that for the binomial distribution, the variance is NPQ and the mean is NP. Since Q is always between 0 to 1, we can say that the variance of the random variable x taking a binomial distribution is always less than the mean of that random variable. Let's look at another distribution called Poisson distribution. It's one of the single most used in the discrete random variable world. It's generally used for counting, for example, number of emails received in an hour, number of earthquakes in a year in a country, raindrops in a given area over time. Even though the individual probabilities are very small, for example, raindrops in a small area over time, but if you accumulate over time, then you will have some results that is non-zero. So it's a more general case of the binomial distribution where n is very large and p is small. So the probability of raindrops falling on a very small area is zero, almost zero. But if you repeat the trial for a large enough time, then you will have a non-zero probability. The Poisson distribution also allows for different p for each trial, unlike the binomial case where p was fixed for each trial. Let's look at the probability mass function. So it's given as e to the power minus lambda, lambda to the power k divided by k factorial, where lambda is called the rate parameter, and sometimes in some books you'll see lambda written as lambda times t. So here we're assuming unit time, but you can also consider lambda times t, where t is the time interval. Is this a valid PMF? We can test that easily by doing the summation. So summation of e to the power minus lambda, lambda to the power k divided by k factorial. Now this is the Taylor series for e to the power lambda. So e to the power lambda times e to the power minus lambda, which is 1. So this is a valid PMF. And the Poisson distribution looks like this, depending on the value of the rate parameter lambda. It's a discrete distribution, but we are showing the envelope of the distribution, so it looks continuous. Let's look at the mean of the random variable with Poisson distribution. So the formula is given, so we replace f of k. So it's summation of k is equal to 0 to infinity k times f of k. We can take lambda and e to the power minus lambda out, since they don't depend on k, and we replace the summation from k equal to 0 with k equal to 1, because for k equal to 0 this term disappears anyway. Now this is the summation for e to the power lambda again, and if you replace e to the power lambda here, then you get the mean as lambda. For variance, we need to calculate the expectation of x square. Now here we have to use a trick where we start from the Taylor series. So Taylor series is e to the lambda is equal to the summation of lambda k divided by k factorial. And this term is similar to this term except it has a k square. E to the power minus lambda doesn't depend on k, so we can always take it out. But we need to get k square from here. So one way to do that is to differentiate this series with respect to lambda and try to get k square term in the summation. So if you differentiate with respect to lambda and multiply both sides by lambda, you get lambda e to the power minus lambda. This will be k lambda to the power k minus 1 divided by k factorial. Then we multiply by lambda, so we get lambda k again. So we got 1k. Now we need to get k square. So let's differentiate again. So if you differentiate with respect to lambda again, both sides, the left hand side becomes lambda e to the power lambda plus e to the power lambda, which is using the chain rule. And the right side becomes k square lambda to the power k minus 1 by k factorial. So we got k square that we are looking for here. So now we can write e to the power e to the x square, or expectation of x square, as this, which is equal to this term lambda e to the power lambda plus e to the power lambda, and the remaining term is e to the power minus lambda here. So we have that here. So if you solve for this, then e of x square will be lambda times lambda plus 1. The variance of x is e of x square minus the mean square. The mean is lambda. So if you substitute that, you get the variance as lambda. So the variance and mean of a Poisson distribution is lambda. Poisson and binomial distribution, we saw that binomial distribution converges to Poisson for large n, which is also equivalent to a small p. And Poisson distribution can deal with weakly dependent trials and allows for non-binary values of x, unlike the binomial distribution. And since in Poisson distribution we don't need to calculate n factorial in n choose k of the binomial distribution, so it's more computationally tractable. So those are the two discrete distributions we discussed in this class.